In this video, we're going to cover some similar content as previous Grasshopper videos, but this one is going to include some Boolean operations, which in Grasshopper are called solid operations. So we're going to structure this pretty similarly as previously, where we build a point in space, build a curve from there, and then construct a volumetric geometry around that, and then perform these Boolean operations to give you another idea on how you might use Grasshopper to variably control design outcomes. So we can go ahead and get started by opening up our Rhino interface, and like always, type Grasshopper to open up the Grasshopper window. When the Grasshopper window opens, we can just go to File, New Document. I'm going to change our Rhino viewport as well to shaded, just so that when we have geometry that we bake in, we can preview that in shaded view. So in our Grasshopper window, as I mentioned, the first thing we're gonna do is construct a point, as we did in the previous videos, draw a curve from that point. We'll do it slightly differently than the previous videos, but this is just to kind of repeat certain content so that we get a firm grasp on these ideas. And this time we're going to use the curve by itself to construct geometry. So not a lofting surface-based operation, but a different type of operation to construct geometry on that curve. So we can start by double-clicking and typing construct point. We can construct an array of points. Instead of going in the x-axis though this time, we're going to construct an array of points stepping in the z with variations in the x and y, meaning our domain and range are going to be plugged into the z, and then our graph mapper this time is going to be plugged into the x and y. This will ensure that we have something that is a kind of vertical orientation, which we'll get into later on when we look at the Boolean operations. So to start that array of points, we just need to double-click and type in range, and we can get a range component, which we can plug in to the z. Now you can see our points have already been constructed there, but we now need to adjust that domain by typing construct domain, and we can grab that construct domain component, plug it into our domain input, and we'll now use two panels to define the minimum and maximum of this domain. So our minimum we can do is just 0, and we'll basically start this curve at the origin, so 0 there. And then our maximum for this domain value we can say is, we'll do 20. Okay. And now for the number of steps, right now we can set that to 20. So we'll just copy this. We could also make this a slider. I guess that keeps it consistent with previous videos. So let's go ahead and make this a slider. 1 is less than 20, and then we can plug this in to give us a slider of those points. Okay, so that controls our z values, and now we just need a graph mapper. So we want to plug in those z values into the first input for the graph mapper. And then we can set a panel just so we can preview what that data translation looks like. Okay. Now we need to set the graph type. So I'm going to right click, go to graph types, and then sign. And then we need to change this domain if we want it to match our domain here for the x's to range from 0 to 20. Now this is saying x just because the graph mapper is a 2D mapper, but we can understand that the x is actually what we're plugging into our z input. So that doesn't actually matter. X is just input and y is just output. That's all we have to know relative to the graph mapper. Now our y we can change from 0 to 1 to negative, we'll do -4 to 4. And that will give us some range to move in that y-axis so that we have a total range of 8 for this curve to move. We could even increase this if we needed to. Maybe it makes the most sense to do -6, just so it's a little bit, it's now over 10, so it's over half of the domain of the X inputs, or that Z domain. So we'll see based on what we get into in this video, but I think that will end up working out for us. Okay, so those values are remapped from -6 to 6, which is great, and then we can just copy that, and we can now just plug both of these graph mappers into the X and Y. So right now it's immediately distorting that the same in both axes, so we get this diagonal array of points. So as we start to make adjustments here, we can get it to the middle so that the 0 maps to 0, so that we can start from that midpoint, and then we can get this kind of twisting. Okay, by distorting both the X and the Y axis at slightly different periods. If we wanted to, we could also change these graphs, the graph types, to maybe something like Bezier, which might be a little bit easier to control in this example. But we can always do that at the end and come back to these graph mappers, right-click, go to Graph Types, and then select from any of these if we deem or expect one of these to eventually be easier or better to coordinate for something down the line. Okay. For now, though, this should be fine. So we have these points. Now, just like previous videos, we want to make a curve. So I'm going to make a NURBS curve from these points. So plug in those points into the vertices input to the NURBS curve. We have a degree 3 NURBS curve drawn not through exactly those point positions, but using those points as control points. And as we decrease the steps in our range, we get smoother curve that is possibly even more dynamic, actually, because it can actually depart from those control points a little bit more. So maybe I'll keep that step at 8 for now, so that we get a smoother transition between these points. Okay, so now that we have that curve, what we're going to do is divide this curve, so the new curve, no longer focusing on these points, so I'm going to turn those off. Divide this curve into a number of points, which we did in the bonus content video. Actually, we did in both of the previous parametric demonstration videos. So we're going to divide this curve into points using the divide curve command. And then with this component, we're going to plug our curve into the curve input. And then we have an option for the amount of segments. So I'm going to make a slider from 1 to 16. And we're going to plug that into the count input. So right now we just have one division, which gives us 2 points. And now we can scroll this up to get higher resolution divisions. Okay. So instead of using this to loft with another curve, what we're going to do is basically construct a parametric sweeping function inside of Grasshopper. So we're not going to use sweep. We could very well use sweep, but to get this kind of parametric control or finer grain control, what I tend to do is build up these curve divisions and actually manually place the sections along this curve so that we can rotate each individual section, getting twisting or scaling actions happening throughout the section. So that means we could taper at any moment, or we could expand at any moment, and it makes these sweep actions incredibly dynamic. So the first thing we want to do is convert these divided points, or rather divided point parameters, as we'll see in a moment, into a series of frames. Now, we're going to need frames because our eventual operation is going to be to orient along this curve on every single one of these points a series of sections. So just to kind of prove why we would do this or what we would do, I'm going to go ahead and bake this NURBS curve. And we can bake the points as well. And then we can take a look at this inside of Rhino. So if I drew a circle in Rhino, and I wanted this circle to move from where I've drawn it here, from its current location, its base location, to my curve, so that I could loft through these profiles on the curve, what I would do is I would type copy, and I could copy from the centroid, so object snap centroid on or center on, to each of these points. And I'm going to just continue copying all the way up the section of this curve. And now we could just select all of those curves, type loft, enter, OK, and we have our lofted sections. That would work perfectly well. The only issue is if this curve was actually tilted or kind of bowing at the top, those sections would still always be facing up. That circle would always be in the X and Y plane. So if instead we wanted to actually orient this relative to the perpendicular frames along this curve, we need to use something in Grasshopper called the Perp Frames. So this allows us to kind of read or register something related to the tangent along the curve, which is going to be a perpendicular frame where the z-axis of the frame or plane is going to equal the tangent of the curve. So we can make this by double-clicking and typing Perp Frame. Now we have Perp Frames or just Perp Frame singular. We're actually going to use Perp Frame because this takes an input curve. So we have that in our NURBS curve. So I'll go ahead and plug that in. And then an input parameter. Well, maybe you get the idea of what we're kind of going for here when we were constructing one singular point. And then when we feed in a list of data, right, a list of numbers into the point, it doesn't construct one point, even though it's a singular construct point. Instead, it constructs many. So although this is Perp Frame and it reads in one singular parameter, if we feed in multiple, it's going to draw Perp Frames on all of those data points using that same curve input. So this is exactly what we want, and we can just take this little t and match it to the little t, which stands for curve parameter. So I'm going to plug that in, and we can see our perpendicular frames drawn all throughout the sections of this curve. And you can see how dynamic that is versus just copying XY planes on every single one of these points. So already we have that kind of dynamism that Grasshopper is enabling us to use. Okay, now what can we do with these planes? So I mentioned that we would take a circle and copy it if we were just doing it in Rhino. But what we can do here in Grasshopper is actually use Orient. Now, why I wouldn't use Orient in Rhino is because I don't have access to these perpendicular frames. If I did have access, I might use Orient to be able to actually get the tilt and rotations of those cross sections. So if I double click and type Orient, we can take a look at what Orient requires. So it takes in an input of a base geometry, so that's going to be our cross sections, and then an input initial plane. Just like when we copied, we needed to use a reference of the center point, so that initial plane is going to be a reference relative to our cross section, and then a final plane, which we're going to use as all of these perpendicular frames on the curve. So let's go ahead and just start setting this up. So our cross section, we can just use a rectangle for now, and we're going to keep this parametric and make this rectangle inside of Grasshopper. Right now, it's probably drawing a very small rectangle. If we hide all of these previous components, we can take a look at that rectangle. The rectangle is previewing also a plane, and we have this grid showing, so let's just hide that grid, and now we can see that rectangle showing up right there. By default, the rectangle is set up on a base XY world coordinates plane with an X size of -1 to 1, meaning it goes from -1 to 1, and a Y size, or Y values, from -2 to 2. So it's twice as long as it is wide. So we can keep this, and we do want it centered around the XY. So we'll just go ahead and use this rectangle. So if we just want to use this, we can just plug it directly into our geometry, since that's the geometry that we want to array. Now the next thing we want here from this rectangle is just a parameter which tells us that the base of this is the XY plane. So we can just go ahead and type XY, and Grasshopper has a default parameter which is the XY plane. And since this is at the origin, we can just leave this at the origin and plug it into the A. Now, if for whatever reason this rectangle was built somewhere other than the origin, we would just need to provide that input in both the input plane to the rectangle and the input origin or input plane to the A input, which is the initial plane. But since it's structured around or built around the origin with the XY plane, we can just leave that as our input. Now, if we go ahead and plug in all of these perpendicular frames into B, it's going to take that rectangle and copy that one rectangle referencing the XY plane from that XY plane and orient it, copying it to every single one of these perpendicular frames. So if I go ahead and hide the preview on these, we can see that rectangle copied along those perp frames. Now already we can go ahead and double click, type Loft, plug in all of these cross sections in, and we get a lofted geometry, which we could then double click, type cap holes, and then plug in that lofted geometry, and we could create or bake out a polysurface closed geometry. So we have one closed polysurface, which can already be used in Boolean operations just as it is. So if I wanted to now rotate this baked geometry or scale it up and then select it with itself, type Boolean intersect, we can get that intersection geometry of both of these parametrically developed and then baked kind of swept geometries on themselves. So already it has some really nice intersections happening that kind of divorce it or separate it from its roots in this pretty simple swept or lofted set of cross sections across that parametrically controlled curve. So already doing something pretty interesting with not much work there. Another way of doing this, though, is to actually set this up all parametrically. So not only can we perform the Boolean operations parametrically, but we can perform additional distortions to the cross sections parametrically. So I'm going to go ahead and do the deformation part first, and then we'll take a look at duplicating this whole thing to look at some of the Boolean operations inside of Grasshopper. So what we need is to look at basically this orient operation and see where in the orient operation we could perform something like a rotation of the cross-section, or where in the orient operation we might perform a scaling operation. So if we wanted to rotate this first, we can double click and type rotate and preview the component for the rotate command inside of Grasshopper. So this rotates an object in a given plane. Well, the object we want to rotate are going to be these sections that we've already placed on our curve. So we know that that's the geometry we want to rotate. It looks really off, and now it's skewed from our curve, and that's because the input plane is our world XY plane. If we put this rotate command before the orient and we rotated just this rectangle, we would see the entire profile before our loft rotate. So I can show you what I mean by that by just moving this rotate here, and we can take this rectangle, we can plug it into that rotate command, and if we just take a look at those two, we can see that it's a bit hard to tell here, but it's rotated 90 degrees. And if I go ahead and turn that preview off, and we just plug this into the geometry, we should see that swept geometry rotate 90 degrees, which it does. So that's fine, we can do that, but it's not quite giving us that finer tuned control. We want to be able to rotate every single one of these oriented sections, so get that level of control. In order to do this, we need to plug in all of the oriented geometries into rotate, and then instead of using the XY plane, we actually want to use the perpendicular frames themselves. So this gives us every single plane, or every single section, rotated 90 degrees around the plane that it's on itself. And now if we plug this in, it's basically going to do the exact same thing that we just had, so not terribly exciting, as just rotating them all by 90 degrees. But this is going to give us many more, so 12 different options to change the angle of in order to rotate them all separately. So what we want to do here is find some way of controlling this angle so that along the parameters of this curve, we can change the angle value to rotate it differently. And then we can use these rotated cross sections to plug into our loft. So what I'm going to do is I'm going to use these parameters. And if I make a panel here, we can take a look at this data. And as we did in previous videos, we don't necessarily know the extents of this data. We don't know the bounds of this data. So we're going to need to perform some operations to normalize this data, making it from a range of 0 to 1 instead of 0 to 6. We can do this by using first a bounds component. This gives us the bounds, or the minimum and maximum values. So if I make another panel here, we can look at this panel, and it gives us a range from 0 to 6, 0 being our minimum in this data, 6 being our maximum. And now we want to use a remap component to remap these number values to 0 to 1. So remap takes in input values. We're going to use our parameters. An input source, we're going to use our bounds. So that's remapping relative to its current domain. And now it's going to give us a range from 0 to 1. Well, if we just plug this into our angle, that's going to give us from 0 to 1 in radians for the rotations. Now, I personally prefer to think about angles in degrees, so I'm going to right-click on the angle, and I'm going to select degrees to change the input there into degrees. And now we can see that instead of 90 degrees, it's using this radian value of 0.5 times pi, so about 1.5, or a little bit higher, as an input in degrees. So that's not very many degrees, which is why there's now just a subtle rotation applied. So if we just plugged in this remapped value from 0 to 1, then it wouldn't do us much good in that rotation. So if I go ahead and plug this in, we can see that that barely rotates along the extents of the curve. If instead I use a multiplication component and we multiplied every single one of these values, instead of ranging from 0 to 1, we multiplied every one by 180 degrees, so multiplied by 180, and we plug in that 180, we now have a range from 0 to 180. So this is another way of kind of remapping this domain, and another way to do it would just be to change this target. Instead of from 0 to 1, we could set it to 0 to 180, and that would give us these exact same values. So either way works perfectly fine. We're going to keep the target at 0 to 1 because we'll go through that in a moment. But if I now took the output from this multiplication component and plugged it into angle, we can now see that we have, starting from no rotation, and then we go all the way to 90 at the middle, and then it goes all the way to 180, which basically looks as though it hasn't turned at all. And that's just because it's done one full, half turn relative to all of the angles, but since it's a rectangle, there's a degree of symmetry, so it only needs to turn 180 degrees for it to be an identical cross section. If we plug in these rotated cross sections into our loft, we should see that twisting actually happening across the section of our curve, which we do. We can now hide those other cross sections, and we can see that twisting. We still, though, don't have very much control. We're just reading in the parameters and then using those as rotation values. Maybe from previous videos you get an idea of what we might be up to, but we can take these parameter values from 0 to 1 and we can plug them into a graph mapper to give us control over these rotations. So I'm going to go ahead and delete this multiplication and delete these panels as well. And we're going to take these 0 to 1 values, plug them into a graph mapper, which has a default domain of 0 to 1. I'm going to go to graph types, and we can select Bezier, and I'm going to plug the output into angle. Now, the default output here is still going to be 0 to 1. So we want the default input to stay 0 to 1 to match our remapped values, but the default output we want to be that 0 to 180. So if we want that, we can double click on the graph mapper, double click on the maximum for our Y value and change it to 180 degrees, and then hit OK. And now we get that 0 to 180 twist. And now as we move this Bezier curve around, we can actually dynamically control the twisting across our section. And if we select that cap geometry, right click and select bake, we can bake this geometry into Rhino. So now we get much more dynamic cross sections across our curve with pretty limited or easy control. Not so much limited, we do have that fine grain control, but easy control. Okay, now one other operation we might want to do is to actually vary the cross section itself. And we can do this by scaling. And we're going to do a very similar operation here with a graph mapper as well. And we're going to take these rotated cross sections and we're going to just use a scale component. Click on that scale. This takes an input geometry, so we're going to take that output from the rotation and we're compounding this effect by feeding that output into our scale output. It takes an input center. Well, that input center is just going to be wherever these perpendicular frames are, which another way to get the center of those perpendicular frames is to just take the actual points that we divided along that curve. So we can take those points, plug them all the way into our center input for the scaling, and then it's asking for a factor, so this is going to be a fraction or a decimal relative to a percent value, meaning 0.5 is 50% scaled. So it's scaling it down by half, 50%. So what we want is a dynamic range of numbers from 0 to 1. This to me sounds like we need a graph mapper. So if we use this graph mapper, we can take these parameter values from 0 to 1, plug them in. We can right click, go to Bezier to set the graph type to Bezier. Now we can leave this default value from 0 to 1 to 0 to 1, giving us a range of scalar values from 0 to 1. And if we plug this in, we get an error because right now we have a value which is actually 0 scale, which is impossible. We can't scale something by 0. So we have to just move this up, and now it gets rid of that error. And you can see that at the very beginning, we have a very tiny, very small scaled cross section, and at the end we have a very big one. Now, as we move these towards the middle, we get closer scaling to 50%, and as we move them all towards the top, we would get a thicker middle and a thinner set of ends, so it would taper towards the ends. If we plug the output of these scaled cross sections into our loft, now we get that tapering as an output in our capped loft geometry. Now we can just go ahead and hide those cross sections, and we can just preview that capped geometry. So now that we've made one, if we just go ahead and duplicate some of these components, so we don't need to duplicate all of them. We do want to duplicate this first set. And we want to duplicate everything but the rectangle, because we're going to use the same cross-section. If you wanted to try a different cross-section, you could just duplicate the whole thing and replace that rectangle for some other geometry type, but I'm going to keep that the same. And we're also going to copy the cap as well. So I'm going to select everything but the rectangle and that XY plane, copy it all down. Now we have a geometry that is exactly the same. So we can go ahead and change the curve first. And then at the end, we can go and take a look at this cap geometry. So what we're doing right now is we're just making two separate caps, but we're not actually relating them together. So if we wanted to relate these two things together, what we might want to do is perform a Boolean operation. So just like we did in Rhino, we can double click, type solid. Here it's called solid intersection instead of Boolean intersection. We can plug one of these caps into A, the second into B, and it performs that intersection. If we hide these previous geometries, we can now see the resultant intersection of these two geometries. If we wanted different control than these sign controls, as I mentioned before, we might want to right-click, go to Graph Type, and select Bezier. So if we select Bezier for all of these, we'll see that the overlap is exactly the curve. So it's a majority overlap here. And this is because our curves are almost identical. So what we might want to do is bring each of these geometries or each of these starting curves closer to that kind of middle range of deviation, so closer to 0 where they're more vertical lines. And we can start there, and then as we subtly move these inputs, we can just change a little bit the kind of clipping that occurs from that intersection. Another thing we can do is change this range of scaling. Instead of from 0 to 1, we may actually want this to be ranging from 0.5 to 2. So I'm going to double click here and change this Y value from 0 to 0.5 and from 1 to 2. Now if we preview this geometry, we can see that that's much thicker. And if we did the same thing with this geometry up at the top, change this to 0.5, and then an upper bounds of 2 for this scaling graph mapper, we now see a much larger, thicker geometry that is resulting. And that's just because we have more overlap and more mass to start with. And as we change the curves, we change how those are clipped. And if we go ahead and bake this, we can preview what that geometry looks like. So we're getting some really interesting, like cross-twisted clipping happening at the base, and then it's more unified towards the top, but tapers towards this point, which I think is looking really, really nice and dynamic, and we're having a pretty easy time controlling this as well. Okay. So another thing that we might want to do, instead of just going straight to intersect, or maybe first performing this intersect, is we could copy this and make another set of two curves. And with these curves, we can join them into this solid intersection. So I'm going to go ahead and maybe just move this baked geometry to the left there. And we're going to copy this whole operation, so all of these components, copy them down. And the only reason why we're copying so many is just so that we can have the kind of control of all of them individually. Now, you don't necessarily want to be just copying or duplicating components like this, but it gives us a good degree of control on the operations that we're hoping to perform. Maybe another way actually of doing this so that we can avoid just duplicating, just to kind of prove a point that it's always better to try to build off of your previous work, is going to be to take these rotations and then build a separate set of lofted sections with different rotations and scaling. So what we can do to do that is just take this set, build off of the same base curve, duplicate just the rotations and scale. Just to double check, we can preview that. And then just adjust the graph mapper alone. Now we can take this and join it with our intersected geometry using solid union. And what solid union wants is just a merge list, so all of our information before it that we want to combine in. So we're going to plug all of those into a merge component, so our intersection and our cap geometry. We can then hide both of those, take this merge, plug it into solid union, and then hide the merge. And now we can go back and adjust these rotations. And adjust the scaling as well. So I can scale up this union so that we thicken the top actually after that intersection. So it has a more kind of frontal face to that top. Now we can go ahead and bake this output and put it right next to the previous one. So we're starting to get a little bit messy here, but we're also getting some really nice kind of almost clamping type of geometry happening at the sides there. So I think besides, these messy bits here, which in the first Rhino video showing Boolean operations, I did discuss how to clean those up. So just keep that in mind. You can go back into that and bake this geometry and then clean it up. But we're getting some really amazing kind of geometric types or features resulting from these operations. So the last thing I want to show in this video is just taking a volume, which in this case we can just draw out a box. And actually I'm going to be a little bit more precise here. I'm going to draw out a box from the origin, and I'm going to do, we're going to do a little bit less than half, so we'll do that value of 6, 6, and then 20. And then I just want to move this so that it's centered around the origin, so -3, which is half of that 6 value, and then -3 again. Now we're going to take this box from Rhino, we're going to set it as a brep inside of Grasshopper, so set1 brep, and now I'm going to intersect this brep with the union geometry that we have from Grasshopper. So I'm going to intersect it using solid intersection, and then plug in our union output and our brep geometry, and then hide both of these. And then I'm also going to hide the geometry inside of Rhino so that we can actually see what that preview looks like. So what we're essentially doing here is we're capping that geometry so it no longer lands on a point or meets the sky in a point, but we're taking that box and bounding it on its side so that it has controlled bounds to kind of clip and reunify some of that complex geometry. What I'm going to do before I bake this out is try and get rid of some of these kind of complex pieces that make a bit of a mess, and then we'll go ahead and bake that output out and save this file. So if I come back here, we should be able to maybe make the scale slightly smaller. There we go, slightly smaller, and now that's nice and clean. And now we can go all the way back to this solid output, right-click, bake. And we have this kind of clipped version of that geometry, and it's much cleaner than the one to its left. That's all for this video. So it gives you a basic idea of how you might use Boolean operations inside of Grasshopper, but also a more volumetric rather than surface-based way of thinking. In the next video, we're going to be getting into a basic introduction to Python scripting inside of Rhino.